Hello and welcome to this Climate 201 episode from Physical Attraction. This is the last negative emissions technology that we'll be covering as part of this series, direct air capture. And it's going to sort of spill over 2 episodes, and then I'll devote the latter half of the second episode to conclusions for the whole series. Direct air capture for CO2 essentially does what it says on the tin. You are essentially building devices that aim to capture CO2 directly from its ambient concentration in the atmosphere. There are several proposed techniques and materials that can achieve this, but in essence you can think of the general high-level process as similar to that in carbon capture and storage, which we covered a few episodes ago, from a fossil fuel power plant or industrial unit, but in open air instead. So you have some scrubbing substance which reacts with CO2 in the atmosphere and chemically binds to it. Once this substance has absorbed the CO2, you then treat it to break those chemical bonds, often by heating it up, applying pressure, or occasionally through a chemical reaction or using water, for example, to extract the CO2 in a highly concentrated form. That highly concentrated CO2 then undergoes the standard CCS procedure that we've discussed before. It's pushed through pipes underground, either to be utilised or permanently buried. Since we're talking about trying to use it as a form of negative emissions, of course, there are many of the major utilisations you wouldn't want to see happening. Clearly, if you turn the CO2 into synthetic fuel and burn it, or use it to extract more oil in enhanced oil recovery, the whole process is not going to be a source of net negative emissions. Realistically, if we're talking about negative emissions from this technique then, you need to include some long-term sequestration plan, which will probably be injecting the CO2 into rock formations underground as before. There are 2 main techniques which have seen widespread research. One uses a liquid scrubber, typically a caustic solvent substance like sodium hydroxide. If you blow air over that solvent, it will react with the CO2 in the air to produce a carbonate of sodium. Then you can heat that carbonate up to release the CO2 again in a concentrated gas stream, and you can reuse the solvent. Or alternatively, you can use a solid sorbent instead. These are often kinds of plastic. Essentially, the procedure is similar. It absorbs the CO2. You treat it with heat or moisture to suck the CO2 away again so that you can reuse the scrubber, and the cycle goes on. The classic example of this is the type of artificial tree developed by Klaus Lackner, which is generally credited as one of the first serious proposals for direct air capture of CO2 in 1999, and he's been working on it for some decades. Lackner himself is widely credited by people in the field with really having founded serious study of direct air capture, and has been involved in advocating its use and developing his own solution for several decades. Radiohead fans like myself might picture an actual fake plastic tree, but these days the devices look a little bit more mechanical. Imagine rows and rows of strips of this particular polymer plastic, fanning out to cover as much surface area as possible, and you're closer to the mark. Typically, a lot of the fancy engineering goes into building these things. It's to ensure that you can really maximise their surface area. Think a little bit like a catalytic converter where you want to maximise the surface area of gas blowing over your surface. And in this way, a gram of these metal organic sorbents can have as much as a football field in surface area in the way that they're folded in on themselves. As wind, or fans, carry carbon dioxide in the air across these polymer strips, negatively charged ions bind with the gas molecules and convert them into bicarbonate. The machine then retracts, pulling those saturated strips back into the container and pumping it full of water. The water begins converting the bicarbonate molecules into carbonate ions. As the water drains away, these compounds become unstable and turn back into carbon dioxide in the air within the container. So now you've got carbon dioxide-rich air, and you can suck that out of the machine and send that on to be treated and sequestered. And then the cycle can begin again. So much for the how of how you can do these things, but we're obviously here to talk about whether it's a good idea. On the face of it, again, we know that the technology does work. There are prototypes at increasingly large scales which are operating today, which we'll talk about later. As ever though, the problem is actually scaling up the solution, at which point, say it with me now, you run into Hornigold's law. To make a real difference, to shift billions gigatons of carbon around, you need to develop an industry on a vast scale. No amount of cleverness will let you have nearly all of industrial civilization running on fossil fuels, and then to solve the waste disposal problem in a cheap or easy way. You're going to need a huge surface area of solvents, pulling in billions upon billions of molecules if you want gigatons to be drawn down with this method. Or to put it as the authors of the CDR primer do, quote, "High-quality CDR will require an extremely large amount of land, energy and resources, and thoughtful long-term stewardship practices. Claims to the contrary are not grappling with the actual size and timescale of the problem." Just as there is a part of all of us that wants to believe that natural solutions to climate change or to negative emissions must be the best, there's also a part of us, and some of us, that believe technological solutionism too. We want to believe all technologies grow exponentially, becoming very cheap, ludicrously efficient. But in this case, we are running up against thermodynamic limits associated with just how easy it can be to physically move this stuff around, to bind, remove and bury CO2, which is almost always going to require building up a very large infrastructure physically and expending a lot of energy. And both of these things can get expensive. If we had abundant clean energy readily available that was too cheap to meter after all, maybe we wouldn't be having this problem. And much as the analogy to CCS shows that the technology can work, it also begs a rather obvious question. Around 0.1% of our CO2 emissions are currently captured and buried with CCS, a number that has taken a decade to double despite a good deal of investment into the technology and lots of hype around it. In these CCS plants, we're extracting CO2 at very high concentrations from the top of flues and chimneys, where, for example, coal has just been burned. Yet for almost every coal-burning operation on the planet, we can't be bothered to extract and bury CO2 at these high concentrations. The promise of direct air capture is that we, as a society, will instead choose to capture and bury CO2 after it's left the chimneys, at a much lower concentration of 400 ppm in the atmosphere, a process which is obviously going to be much more energetically and thermodynamically expensive, and will require the construction of much more sorbent than you would need, necessarily, to capture it from the flues in the first place. Now, this is obviously not entirely the picture that we need to talk about, because direct air capture can be used to draw down CO2 that comes from point sources. It might be more economical if you have a fleet of cars running around to use a direct air capture plant to draw down the CO2, as opposed to trying to capture it all on the cars themselves. But that's sort of beside the point, while we still have all of these fossil fuel power plants that aren't fitted with CCS. To be really specific here, quoting from the excellent CDR Primer book, which was a big collaborative scientific effort released when I was already halfway through this series, but well worth a read. CO2 in the ambient air is 300 times more scarce than it is when it emerges from a flue of a coal-fired power plant, and 100 times more scarce than in a natural gas plant exhaust. The result of this is that you need 3 times as much energy in the theoretical thermodynamic minimum, and 300 times the surface area of sorbent to achieve the same capture rate of CO2. For this reason, direct air capture will be more expensive in energy costs and capital costs than CCS from industry and power to get the same amount of CO2. And we're barely doing any CCS at the moment, so that gives you an idea of the costs involved here. So in some ways, to think this is going to make a huge difference, you do have to be a bit of a techno-utopian. And it's obviously something we should consider implementing when we've already done a lot of mitigation. As a mitigation tool to reduce emissions while we're still chucking CO2 into the atmosphere, it's a bit like trying to extract salt from a glass of water only after you've tipped it into a full bath. Or maybe trying to do a blood transfusion while you haven't applied the tourniquet yet. It's usually very obvious to people who study this that negative emissions are a bit of a last resort, and there's a great deal you can do which will reduce emissions much more cheaply, but rarely is it more obvious than this. And if you think that CCS is never going to take off and we're never going to inject billions of tons of CO2 underground, then you might be even more sceptical about direct air capture being responsible for a significant proportion of our mitigation effort. There is something quite techno-utopian about a lot of these proposals. We have these dreams of vast fleets of artificial trees humming away to undo our historical damage, powered maybe by fleets of nuclear reactors or vast arrays of solar panels in the Sahara Desert. It's a bit of a sci-fi vision, and reminds me of Professor Rockstrom's idea of a spaceship Earth, which we discussed with Professor Willis. If we really could treat the Earth like a spaceship, this pale blue dot of a habitat hurtling through a void that is desperate to kill us, then direct air capture would be the exact sort of thing we'd do. After all, then it's just the mechanical air filtration system that keeps our own waste products from building up and killing us over time. But we're not on a spaceship, just our natural habitat that we're slowly degrading. And anyway, it's not entirely clear who's flying this thing. However, having torpedoed the most starry-eyed of the techno-solutionists, I should talk about why we can't dismiss DAC out of hand entirely. The first reason, of course, is that, like all negative emissions, it actually allows us the opportunity to hope that we can reverse climate change, whether after we overshoot a temperature target like 1.5 or in subsequent decades. And there are sectors that will be very difficult to decarbonise, including things like aviation. This is the killer app for negative emissions in general, after all. But it's also the pragmatic slippery slope that some climate purists will hate. But if it boils down to whether it will be easier to ban flying entirely or ensure that the cost of flights include burying the CO2 emitted by that flight, it's hard to say that banning flying outright will be more feasible, and therefore net zero is going to need negative emissions. And there will be plenty of people keen to apply that same logic to their own pet sectors where alternatives are expensive or hard to deploy. I do also think, again, for negative emissions, I should emphasise the niche associated with the convenience of it. So the UK, for example, our per capita carbon footprint is around 5.3 tonnes per person. Now, I don't think climate change should, or is, a matter of responsibility for each of us personally. It's something that requires predominantly collective action to change the carbon-intensive systems that operate around us. And sometimes personal responsibility can be used as a mantra to try and thwart that collective action, as we discussed in the episodes on discourses of delay. After all, the airlines will cope just fine if 1% of people choose to never fly again because of the climate, but there are no broader regulations to force them to curtail their pollution or clean up their waste. But with all of that said, as an individual, imagine you're faced with a choice. Try to live a completely zero carbon lifestyle, which is going to entail significant and perhaps impossible changes. Alternatively, you can pay someone, say, $50 a tonne to bury your CO2. For many, it would be tempting simply to make that payment, assuming that such an option is available. And I think this will be true of businesses as well that are seeking to go net zero. And for companies which have even pledged to cancel out their historic cumulative emissions, there's no alternative to using some sort of negative emissions to compensate for that. You can debate the morality or the long-term sustainability of this as an approach, and I'm sure you would have lots of valid points on that. But I think that all of these factors will continue to drive interest in negative emissions in general for a long time to come. But one advantage that direct air capture has compared to other solutions is that it's not quite as constrained as they are. We've talked about, for example, for BECCS, for enhanced weathering or afforestation to make a significant dent, on the order of gigatons of carbon dioxide. In other words, a significant percentage of our annual emissions today. Well, then you need to cover vast swaths of the world's agricultural land to achieve that goal. At least for direct air capture, you're not really competing for that valuable, viable agricultural land, because the land footprint can be a lot smaller. I think the fact that there are perhaps fewer ultimate constraints, even though the technology is more expensive today, is really the key. Because if the ultimate constraints do end up being cost and energy, the enticing factor here is that we might have a much richer society. Or if energy, especially renewables, becomes dirt cheap, then maybe it would be worthwhile to go down this mechanical route rather than trying to conjure more land for BECCS, which we can't just conjure into existence as easily, and which there's going to be a lot of pressures on. And of course, the negative societal impacts of biofuels competing for agricultural land are well documented, as those who listen to my rant on corn to bioethanol will remember. So it's interesting, you don't have this constraint that comes from land use. And even something like enhanced weathering, even some of the solutions that we talked about, some of the out there ones like ocean iron fertilisation, there are sort of fundamental natural limits to the scale that these things are really going to operate on. But at least for direct air capture, you can theoretically say, well, if you're willing to build more machines, you can capture more CO2 from the atmosphere. The main requirement is energetic. And that's not necessarily going to be easy, but there is some arguments to explore around whether you could use some of the excess energy produced by renewables, at times when it might otherwise be curtailed because it's too windy or too sunny, to power direct air capture plants. Already in the UK and other countries, there are instances where oversupply means that the wind turbines have to have their generation curtailed, and the power is essentially wasted. Analysis by a company called LCP suggested that the UK's wind generation was curtailed on 75% of days in 2020, with a total of 3.6 terawatt hours of power that wasn't used. That's mostly due to constraints in the network. So in an increasingly renewable, increasingly networked system, there could potentially be some cheap electricity available at some times. In practice, we might of course choose to charge batteries or make hydrogen with that excess energy instead. And it may be the case that it's not worth building direct air capture plants in order to only run them then when electricity is cheap. This is something that I think people can get confused about when it comes to the flexible grid, which is you have to consider each project from its own project point of view and the cost benefits associated with that, right? If you're saying, oh, don't worry, we're going to have a natural gas power plant or a nuclear power plant that is only going to operate when renewables can't provide sufficient electricity, that's kind of not how it works. They're going to want to operate that plant as much as possible. Otherwise, you've built it and you're not getting as much electricity sales out of it as you could. The expensive bit is the capex of building it. So this idea of plants that just sort of come in and out when needed is difficult. And again, if you have a lot of flexibility on the grid in terms of being able to store energy, it makes things a lot easier. And that is a big part of the attraction of batteries and hydrogen and electrolysis. But, we'll have to really see what happens. I think project level economics, though, is going to be crucial as to whether this is actually realistic. And that applies on the demand side as well when we're looking at direct air capture as being a demand for energy, right? Because if you can only afford to run it 10 out of every 100 days or something, then it's obviously going to capture 10 times less CO2 and it might not be worth building in the first place. Basically what I'm saying is that the price of electricity is not always going to be the constraint on what you're trying to do here. However, it does at least raise something of a possibility for an initial niche application for direct air capture. But one thing that this doesn't do, the fact that energy might be cheaper, is avoid the point of view that obviously energy is still going to be valuable to people at whatever price you're selling it at. And so you're going to need to implement some mechanism which will pay people to suck CO2 out of the atmosphere. If there's no incentive for them to do that, then they won't want to buy the energy to do it, and they won't want to construct the plants to do it. So just the fact that energy is cheap doesn't get around that problem. But you can imagine that maybe direct air capture could sell carbon credits and it might be able to exploit cheap electricity to do so. But as with pretty much every other negative emission scheme, it's hard to see how it can possibly scale to the size envisioned without that really strong incentive to bury CO2 that has to come in somehow. Typically in models, this is through a very high carbon price, a big active market for negative emissions. But it could also simply be mandates or regulations that would require companies to pay for at least some of the CO2 that they're responsible for to be removed from the atmosphere again. If that were to be the case, then you might imagine that they would get very good at doing direct air capture, or indeed contracting it out to direct air capture companies that could physically bury the CO2 at the cheapest price. And then you have the incentive for the industry to exist and to optimise and all of the things that we would want it to do. Speaking again from the perspective of a company, for example, that has been mandated to bury its CO2, I think there is another key advantage for the climate, which is maybe slightly less obvious, but those of you who've listened to the rest of the series will probably get what I'm talking about. I think the carbon accountancy with the direct air capture system is probably a lot more straightforward and transparent and therefore easy to do than in the case of some of the nature-based solutions we've discussed elsewhere. We've talked a lot about, for example, with afforestation or BECCS, that you can have creative accountancy. There are scientific uncertainties about how much carbon an ecosystem is really holding when you attempt to pursue a natural solution to sequester carbon. We know in some cases, like ocean iron fertilisation, that it's not really clear whether the net impact you have on the climate is positive or negative at all. And in cases like that, it's very difficult to know how much CO2 has been drawn down, permanently sequestered. But if you are directly capturing, liquefying and burying CO2, it's very easy to measure how many tonnes of that you've buried. It's going to be relatively easy to calculate the carbon footprint of your DAC activities in terms of making the plant and the energy usage, because it's an industrial process. And then you can just subtract that off your efficacy. So the accountancy, in terms of actually making sure that you genuinely have drawn down CO2 in the amount that you say, is simpler for this system. And that might mean that in a world where people are thinking about these issues carefully, people might value it as a sort of gold standard. I mean, you know that the CO2 has been drawn down in a way that you don't with other types of offset necessarily as well. So with all of those pros in mind then, let's talk about some of the downsides of direct air capture. We've talked about the fact that capturing CO2 from thin air is more expensive than CCS from fossil fuel power plants. But part of the advantage of doing it with fossil fuel power plants or industrial processes is that you can actually use the heat and energy that you're already producing on site from those fossil fuels. In other words, say you're burning coal to produce electricity, you've got a lot of waste heat coming around. You can channel some of that towards your sorbent to break the bonds and release the CO2 so that the sorbent can be reused. You're already producing that heat. But you can't necessarily do that if you're running a direct air capture plant. You're going to have to get the heat from somewhere else. According to surveys cited in the CDR primer, the current estimate is that you need 180 to 500 megawatts of power to capture 1 megaton of CO2 per year. This power would generally be split around 80-20 between heat and electricity. 80% heat, 20% electricity. So the cheap renewable price for electricity might not be actually that important unless you're converting those renewables into heat, say through hydrogen or something like that. That heat again is required to break the sorbent chemical bonds. The electricity is mostly for fans to blow air across the device or create a vacuum pump if vacuums are needed. This doesn't include the cost of compressing and sequestering the CO2 in terms of its energetics, but that's a smaller component. So again, these are the things to think about. 1 megaton of CO2 per year, you'll need a constant stream of between 180 and 500 megawatts of power. Now, a big power plant is about 2 gigawatts. So for every 4 megatons of CO2 you want per year, you need a big power plant to be running and producing all of that heat for you. And that is going to be difficult. The fact that you need a lot of heat in particular is not particularly ideal. We talked in earlier episodes, particularly the energy efficiency and industry episodes for fans of Climate 201, the issues that have arisen trying to decarbonise heat. Most of the processes that we use to generate heat involve burning things, after all. It's theoretically possible to get some negative emissions by burning natural gas to provide this heat. That will give you some net negative emissions in theory, but obviously that would lock in dependence on fossil fuels and reduces the efficacy of your DAC system substantially, so it might not end up being the cheapest way to get negative emissions. You could get this heat with biomass, but then we're back to the land requirement issues with BECCS. You could burn hydrogen, but of course then you have to produce it through electrolysis. There's more steps in the process, and you'll need more initial renewable energy generation at the start, because there's inefficiencies in each step. For low carbon heat that you sort of get directly, maybe you're looking at nuclear power, geothermal power, or concentrated solar power. But each of those is, at present, more expensive than other ways of generating power, and they do also have locational restrictions. These restrictions are explored in the CDR primer, where they explore some of the ways that you might want to tap geothermal wells to power big DAC fleets, or concentrated solar power to power similar things. You could scavenge waste heat from industrial processes or power plants, so you might have a power plant and then run some DAC next to it. But then there's always the question of, are you doing CCS there as well? Well, you should be. And also, this waste heat is also part of our proposed solution for heating homes in the future, especially in cities. And it sets restrictions on where you can put your big DAC plants as well. If you've got power plants and big industrial processes and there's not much area for the DAC, then that's going to be a problem. So there isn't really a very easy solution. There's lots of potential solutions, but there's not an easy and obvious solution to how to provide all of the heat that this requires. Now, I should mention here briefly that there are some intriguing technologies that are being developed that would try to do direct air capture directly from electricity. This would then let you integrate it with really cheap renewables, which can be situated in more locations like wind and solar photovoltaics. So wind and solar panels, we think these are going to be the cheapest forms of any sort of energy, and that will be electricity in the future. So if you had something that worked straight off electricity, it would be nice. There are technologies with fancy names like the Faradaic electro-swing reactive absorption technology. This sort of thing is still being developed at the laboratory scale. There was a paper called Voskian and Hatton in 2019, if people want to read about that. They have shown that it's developed a high Faradaic efficiency and a low energy consumption, but still experimental and still not clear if you can scale it up, and still not entirely clear how this works. It's very new science at the moment. But this is the sort of technology that, if developed, might potentially give you this idea to balance the grid and suck up CO2 at present as a side benefit. But right now, it's mostly just lab prototypes. The CDR primer mentions it, but says that we can't really rely on it being developed, and we can't get really any sense of how it would cost at scale yet. If anyone has any more information about this technology, let me know, because I'd be interested to read about it more. But it's really in the realm of coming attractions at the moment, and that's why we're not really devoting much of the show to the idea of doing it directly with electricity. Again, it's always important to give a sense of scale for these numbers. So let's remind ourselves that for this negative emission technology to make a really significant impact, we're talking about the gigaton scale of carbon dioxide annually. Again, global current emissions are around 40 gigatons a year for reference. To achieve that then, we'd need between 180 to 500 gigawatts of power just for direct air capture. That would be anywhere between 1 and 4% of current global energy consumption to cancel around 2.5% of global emissions. So it's interesting, isn't it, if you actually look at that. To cancel out our emissions from direct air capture, the emissions mostly coming from different types of energy use, it's almost one-to-one. You almost need 2% of our current global energy consumption to cancel 2% of our current global emissions. And that gives you a sense that we're really not getting a free lunch here. It would have to be a significant portion of our energy consumption and our sort of undertaking to do things at a significant scale. Now, of course, maybe we'll consume much more energy in the future. Maybe there'll be much, much more generated by renewables, but again, that's something you have to convince yourself of. There have been estimates that the theoretical minimum energy to capture CO2 is 0.5 gigajoules per tonne, but taking into consideration inevitable inefficiencies and stages in the process, it can rise to 12 gigajoules per tonne. That would again place the price of cancelling out our current day emissions at something not too far off our present day energy consumption itself. So in terms of energy consumption, it's not a free lunch. There was a paper recently called Rail Monti et al. In 2019, which was summarised nicely for Carbon Brief, again, our friends over there. And that actually put direct air capture into integrated assessment models for the first time. Devotees of the series will remember that integrated assessment models are these economic models which try to figure out how to decarbonise in the cheapest possible way, given a whole bunch of assumptions about technology and carbon taxes and so on. You'll remember from earlier in the series that these economic models tend to quite like deploying future technologies due to assumptions about how economic growth, discount rates, and how technologies will develop over time. Typically, these things have had bioenergy with carbon capture and storage in BECCS, and they like that quite a lot for reasons that we've discussed in the BECCS episodes. And maybe at some point I'll get on and do an episode just dedicated to IAMs, but you'll have to let me know if you'd be interested in that. It would be a bit of a departure to get into some of the economics there, but I think because they're so influential on policy, it might be worth it. But anyway, this paper basically says, okay, let them use as much DAC as they want, as much DAC as they can pay for, set a price for the direct air capture, and just say that they can use it. If you don't put a limit on how much negative emissions they can do through DAC, then they produce some scenarios where by the end of the century, it's sucking out 38 gigatons of CO2 a year, or basically all of our emissions in the present day. But doing this would require 300 exajoules of energy, around half of our current global consumption. In the model, the world's energy consumption in 2100 has doubled by then. So again, you're sucking out all of our emissions, but it's costing you around a quarter of the global energy consumption. Of course, in the model where they've decarbonised, other things have happened to reduce emissions, so it is net negative at that point. It's not just a one-to-one cancellation. But the point is, if you want to imagine DAC cancelling out all of our emissions today, it would require half of our current global energy consumption. So doing this at scale does require a pretty heroic quantity of energy, no two ways about that. And of course, this would have to be generated using clean alternatives to fossil fuels. The paper's authors also calculate that if we assume that large-scale DAC will be available, but then it isn't, then the emissions trajectory could put us on track for another 0.8 degrees Celsius of warming compared to the alternative. So that at least gives you a sense of the potential moral hazard here if we rely on technologies that then aren't built, and maybe how much DAC delays mitigation compared to other options. So it's a tricky one, isn't it? You can't really plan for this stuff to materialise at the massive scale that they're envisioning here. This is the sort of scenario that might show up in a model where the world gets extremely advanced and yet we've produced so much clean energy that we can use it to suck out and cancel out a year's worth of present day emissions. I mean, just think about that. Every emission from every car on the planet, every emission from every fossil fuel power plant on the planet, the whole industrial process that we have now, but in reverse. And that would be a component of our economy at the end of the century in this model. It's a pretty wild, starry-eyed future that they're looking at there. For this reason, of course, the sheer energy consumption and requirement for that energy to be clean, you would expect that it will almost always be cheaper and easier from the point of view of reducing emissions, just to use that cheap energy as a substitute for fossil fuels, rather than using it to cancel out emissions from dirty energy. And then we're back to the idea that this is only going to be used to cancel out hard-to-mitigate sectors, like maybe aviation. The reason to emphasise this is to drill home the fact that the scenario where this is a magic bullet solution to climate change and now we've developed technologies that can pull it out of the atmosphere and we're just going to roll that out at the scale that allows us to carry on business as usual, that's not going to happen. And if it did, it would be an immense subsidy to the fossil fuel industry to do things this way. We know that their motivation and modus operandi is to privatise some of the gains and socialise some of the losses by getting governments to pay for negative emissions. It's part of what makes the prospect of talking about them so dicey politically. So once again, these negative emissions technologies do not and cannot substitute for the vast majority of what we have to do in terms of building out an awful lot of zero carbon power, low carbon electricity generation, electrifying everything in sight, like transport and so on, to run this power. Because they actually require us to do these things for them to work. Does that make sense? All of this energy consumption and all this sorbent material, of course, translates into cost. Now, the cost question is controversial for direct air capture and still really being debated. There was a paper from 2011 called House et al. That took a very pessimistic view and claimed the cost would always be very expensive, in excess of $1,000 a tonne. If that was the case, we may as well pack up and go home, because virtually any other kind of mitigation, let alone negative emissions, would be much cheaper than this, and this wouldn't be worth considering. But that paper has been kind of debunked since. It made some very negative assumptions about the cost of energy and capital. It seems that people who have done prototypes have already done it cheaper, so $1,000 already looks much too high. There are prototype units operating which were built more cheaply, and the clean energy is getting cheaper, so at least that House et al. Is too pessimistic. On the other hand, though, maybe you have to rely on estimates from people involved in the industry. David Keith, the founder of Carbon Engineering, that's a company that has developed a pilot plant and started to develop a large-scale direct air capture plant. Of course, the people involved in the industry will give you more optimistic estimates for how cheaply this can be done at scale. For example, in a 2018 paper, he argued that when the industry is scaled up, costs will fall, perhaps to around $100 a tonne, which could start to make direct air capture close to the sort of prices that might be showing up in carbon taxes and other forms of negative emissions. Klaus Lackner of the Artificial Trees, he's been even more optimistic about potential long-term prices for DAC, suggesting lower than $50 a tonne once materials are improved. I don't want to get excessively bogged down in trying to refute individual papers and into the minutiae of how different things will cost, particularly when a lot of it ends up based on opaque assumptions about technologies that we haven't really developed yet, that haven't been deployed at scale yet. But if you really want to get involved in that, there's a really detailed paper called Techno-Economic Assessment of CO2 Direct Air Capture Plants. That reviews lots of different cost estimates for these plants, compares different types of technology and methods of estimation, and so on. And I nearly wrote it up for this, but I figured that it would be just too much information for a brief introduction to the subject. But if you want to get into the detail there's a survey in that paper. However, I think it's probably safe to assume that the House et al. Figure is way too high. Given that Keith and Lackner have interest in the industry, their estimates may be too optimistic as to how rapidly or successfully the technology will develop and bring down costs. Lots of the companies that are currently aiming to deploy this at scale have set targets on the order of $100 per tonne of CO2. I think they think that's reasonable for the next 10, 15 years maybe. And I think anywhere from 50 to 200 in terms of the long-term price would be potentially unsurprising if the industry gets very big, especially if energy gets cheap. But ultimately, the floor is set by that capital cost to build these things, to build this infrastructure, and the energetic requirements in terms of heat. To do this at the scale we're talking about, you would need thousands of plants processing 1 million tonnes a year. Ingenuity and technological development can work wonders at lowering the costs, especially if the industry can mature and does get cheaper through deployment, but they can't get around thermodynamics and the basic, huge scale on which we're talking about moving around material here. If we accept that idea of $100 a tonne for direct air capture then, getting up to our gigaton scale with direct air capture, where we'd be cancelling about 2% of current emissions, that would consume around 1 to 4% of the world's energy use today, and it would cost around $100 billion a year to cancel 2.5% of our current day emissions. That's about what rich countries have supposedly pledged in climate finance to poorer nations. It's about 0.5% of US GDP, or one SoftBank Vision Fund per annum for fans of the show. So again, you have to look at that and say, is that value for money, $100 billion a year to cancel 2% of our emissions? Maybe it is, maybe it isn't. There's certainly people who think that you can mitigate climate change by avoiding emissions and replacing fuel sources in a cheaper way. But perhaps for that very, very hard to mitigate sector, if that would be, say, something like the airplane sector, the aviation industry, has to pay $100 billion a year, could they do it to cancel out their carbon effects and be allowed to continue going? I don't know. So just to say that obviously this is not a free lunch either energetically or in terms of cost. And that's why you almost have to be a utopian believer that we are going to be a much, much wealthier society in the future for us to imagine cleaning up the problem in this way. The CDR primer, by the way, also estimates that this would require perhaps 2,000 square kilometres of land for the direct air capture plants and their power sources if we were going to cancel out a gigaton with this, depending on the type of power that was used. Now, that's not nothing. It's about the size of a UK county or Rhode Island for our American listeners. But of course it pales in comparison to the land requirements that you would need to do this with bioenergy crops for BECCS, or the area that you need to sprinkle rock dust over for enhanced weathering to operate at that gigaton scale. So the land requirement is less, and maybe that will end up proving telling when it comes to this. But again, you look at DAC, you look at that huge expenditure and that huge energy use, equivalent to an industry to cancel out 2 to 3% of emissions. And you can see that this really is going to be a niche for difficult to decarbonise sectors. And it's hard to see it being the silver bullet for climate change. And I know I've said that a lot, but I know there's going to be techno-optimists out there who still think it is that. And I think my primary aim with this whole negative emissions series is simply to say that we can't let ourselves believe that negative emissions are going to easily scale to solve the climate problem. And in fact, when you look at it and when you think about it, it seems like for all but the most expensive things, this is going to be, it's going to be cheaper to mitigate conventionally. And I think that is the message that you get from this as well. Thank you then for listening to this episode in our series on negative emissions. Next episode will complete the discussion of direct air capture as a way of getting negative emissions. And then I will finally conclude the whole series with a few brief remarks about what we've learned and why I think it's still important to talk about this topic. Thank you then for listening to this episode of Physical Attraction. Remember, you can find us on the web at physicspodcast.com. There you'll find links to the Patreon where you can get hold of all of our bonus episodes and early releases of episodes. If you're listening to this early, you're listening to it on the Patreon. Thank you very, very much for supporting the show. I really appreciate it. You'll also find the contact form where you can get in touch with any comments, questions or concerns you may have about the show, future show ideas, people who'd like me to interview, all that sort of stuff. I'm open to feedback and I try to respond to as many emails as I can get hold of. You can help out the show by reviewing us or recommending us to other people. We are a small independent show and we rely very heavily on word of mouth for people who are interested to get the show out there, and I appreciate anything you can do to spread the word. Until next time then, please do, take care.